Good morning, students. I know that we still struggle with health during this COVID crisis, and I still have students who are becoming ill. And so all I can basically say, I've been very lucky myself, but be very careful when you're out and about. To wear your mask and to just practice, you know, safe habits. It's very easy to not think about what you're doing and easily pick up the virus. And the my hope is that if anyone does pick up the virus, that it's a mild case. It varies with person to person, and just be very careful. Don't take anything for granted. I know that we're all weary of this situation, but it's something that we still have to be vigilant about. And hopefully, before too long, there will be some relief in the medical end of everything. So please keep that in mind as you're out and about. I have to remind myself to do the same. Now, what I want to do today is to do some models. We've talked about some models working through the logs and the exponents, but we want to do two particular models today having to do with growth and decay and the Newton law of cooling. So I think you'll find those fairly interesting and probably something you may have touched on in college algebra. And also, I want to share a problem that I actually worked in the conference hours yesterday. But before I do that, I want to share some things with you about what you're preparing to do in calculus. I have a student that comes by the office hours regularly, and this was a problem that he was working on. And the idea here is that this will be something that if you take my Calculus 2 class, I'll teach you how to do. This is called integration by parts. But what I wanted to show you, class, is that once you do the calculus part here, all of this, all the way down to the very bottom, is algebra. And I made the comment to the student, I said, now WebAssign didn't say that you had to format in a beautiful rendition as we arrived at the end. So I said, go ahead and type this in. And of course, WebAssign accepted it because there was no specific formatting. But what I want to show you is, as all the manipulations we do with fractions, the manipulations with factoring, greatest common factor, all of this, you will do every day in calculus. More so depending on the types of topics that you work, but I can't impress upon you how important it is to work through examples. And then after we finish today, we're going to start talking about trigonometric functions. So another question he asked about had to do with the integral of this this trigonometric expression. Okay, once we do the calculus, then we have lots of manipulation with algebra. So the way to calculus is through number theory, algebra, trigonometry. Those are the raw materials, so to speak. So as you put more and more time into this class, just remember that the goal is preparation for calculus. And any lack of motivation in that effort will show itself when you take the calculus. And my hope for my students is that you spend the appropriate time on these topics, so when you set foot into the calculus class, you are ready to go and you will have no issues at all. Again, the whole idea is to have a clean transition. And so that as you learn the calculus, you can apply that to your science classes, your computer science, engineering, you name it, and be very comfortable. Now, before we start with the growth and decay law, I wanted to write down an example that one of your colleagues asked about during the conference hours. This is a WebAssign problem. and I thought it was interesting, so I want to go ahead and do it. So we have a very interesting situation here. We have x minus 1 raised to the base 10 log of x minus 1 equals 100 times x minus 1. This was a problem where there were 3 equations, and WebAssign gave a hint for this one, and I want to go ahead and use it. It said take, and this is one way to do it, and the hint's actually good. Take base 10 logs. And the idea is this would allow us to use the product rule and the power rule. So when we do base 10 logs, we know that in this particular case, that's a base 10 log because it doesn't have a subscript. So let's do that. So the base 10 log of x minus 1, a lot of times I skip some of these steps, not because I'm being difficult, it's because they're fairly straightforward. But here I'll go ahead and include everything. Now, another thing I was noticing with my students yesterday, if WebAssign builds in parentheses as you type logs or whatever, do not delete the parentheses. It will not check correctly. Yesterday I had a student who what I figured out is that he had deleted parentheses about the argument of a cosine function, and therefore WebAssign didn't recognize it. So as you're typing and you use your math palette, if it gives you a left parenthesis, then you leave it alone and you close it. Don't, just realize that if that's part of the algorithm, then you need to respect that. And so just be careful as you do your WebAssign and you type your responses. Follow the formatting, but do not delete anything that WebAssign includes as you type your responses. Now notice we have the power rule. So the power here, which is log of x minus 1, can come downstairs. So we're going to get 2 copies of that. And then, of course, over here, we have the log of a product. Now, WebAssign would stick in the parentheses here. I don't use them because it's not unclear, but WebAssign would put both of these in. So now we have the log of a product, which is the sum of logs. So log of 100 plus log of x minus 1. And of course, we need the parentheses here because it would be unclear if we did not use them, because is the x included and the minus 1 both, so we need parentheses. So that's something I do when I write my notes. But again, WebAssign will throw in the parentheses because that's just the way the computer algebra system is coded. Now notice we have 2 copies of this, so we can write it as a square. And of course, this is the power of 10 that equals 100, which is 2. What's the logarithm? Power of the base. So now, WebAssign is always keeping us on our toes. Now we have quadratic in log of x minus 1. So this is insane, right? So quadratic in log x minus 1. Now, of course, the way we do this is we put everything on one side, and you can see that this will actually factor. Not like the hyperbolic sign that we did last class that required the quadratic formula. That was a harder problem only because it just had more steps, but still very straightforward. Now, if we look at this quadratic in log of x minus 1 by the Professor Ron's lemma AC, we get a 1 times a negative 2. But the sum of these 2 numbers, the z and w, is actually the coefficient of the log term. So that will work. So, and of course, leading coefficient's 1. So this is an easy factorization. So we can use minus 2, and we can use plus 1. So I thought this was a good question and was worth repeating. Again, if there's some problems during my conference hours that are good, I want to share those with everybody. And now we use the zero product, set each of these factors to 0. So we have log of x minus 1 equals 2, or log of x minus 1 equals -1. Now, this is where if we had exponential terms here, then we would say, wait a minute, no real solution. But remember, the logarithm has all reals as the output. And so this is not an issue here. So now we say, what's a logarithm? Well, the power of 10 that equals x minus 1 is 2. So 10 to the 2 equals x minus 1. What's a logarithm? Power of the base. So now x, we just add 1 to 100, and we get 101. Now here, same thing. The power of 10 that equals x minus 1 is -1. So we have 10 to the -1 equals x minus 1. But that just says x minus 1. We could write the 10 to the -1 by definition, which is 1 over 10. So x will be 1 plus 1 over 10. So we just write that as 10 over 10 plus 1 over 10, which is 11 over 10. Now, the thing is that these are both fine here in the log term, because if we replace x with a number that's bigger than 1, the argument is still positive. So both of these will actually work. And I think the student that asked, actually, I think they got this one. They got one of these, but not both, which was kind of surprising. Maybe what they thought, they saw this and just said, oh, there's no solution because of the negative. But again, just remember, the logarithms have the more expansive range. Remember, the logarithm, they say logarithm has the domain of the exponential function as the range. So the domain of the exponential function is all reals. So the range of that, they say logarithm, is all reals. And so that's why this is not an issue here. But again, this is a nice WebAssign problem. And I told the student this would make a good test question. The thing is that by working through examples like this, you really just improve your techniques, because all we're using, aside from the fact that we have to use the identities for the logarithm, we use quite a bit of algebra. And these are the techniques you will continue to use as we work through the rest of this class, and then of course into the calculus sequence. So that's a good example. So thanks to my students for asking about that. Now, what I want to do is talk a little bit about these models. Now, when it comes to modeling, at least at this point, what we can do is write down the actual law, and then, ladies and gentlemen, we can write the solution function or solution curve. We really don't have the calculus means to solve these in a way that we would in Calculus 1 or Calculus 2. So what I'm going to do is write down the law and then show you what the solution curve is. So the first one, so this will be 4.6, and these are just models. Now, when you do calculus, and then maybe eventually some of you take differential equations, you'll learn more about the logistic model, which we talked about in more detail. So for instance, the first model will be instantaneous growth and decay. Instantaneous growth and decay. So now what we're going to do, and of course Newton devised this, and he also devised the cooling laws. So Newton was our hero with these laws, as he was with many things about math and physics. Now, what we're going to do is say, and this will be the notation I use, and the notation varies from problem to problem. So be sure to use the letters that the problem uses. And usually most of the independent variables will be t because these will be time dependent. So y of t will be a quantity. A quantity, you know, maybe it's some a radioactive substance, the mass of that, you know, might be a population, it could be anything. A quantity that is time dependent. Time dependent. And what we're going to do is we're going to let K correspond to a constant of proportionality. So what I want to do is actually write down the given law. And this is a very famous law that is used widely in math and science. Basically what we say, and this is calculus notation, the instantaneous rate of change of y with respect to time. That's called a time derivative right there. Sometimes it's abbreviated y prime. Is actually, the law is actually saying that this instantaneous rate is proportional to the quantity y. And when we say proportional, there's this constant of proportionality there. And what we say is that when time t equals 0, and I'll just say t measures time. And of course, the time could be in minutes, seconds, years, whatever the problem says. So we're going to say that the initial quantity is y sub 0. That's usually a notation that's fairly popular with these kinds of models. Again, if we were using an n here, we'd write n sub 0. So that doesn't matter. I mean, again, the notation can be specific to the actual problem you're working. Now, this, again, you will be able to solve when you take calculus, and the solution curve looks like this. And this is what we'll use in this class. So when you solve this, and this can be solved by integration, we get the following solution curve. Y of t will be the initial amount, y sub 0, times e, that's the standard, the natural base, to the kt. Now, what we normally call this law is an initial value problem. That's another phrase. And again, things can be given with different hypotheses. Let me write that so you can see it. O kind of got lost. So when you think about these types of examples here, sometimes the initial conditions or the hypotheses can vary, but most of these types of problems will be given with this kind of information and some type of an initial value here. And so when we try to work with a solution curve, we would see that we would really need to know the initial amount here, and we would actually need to know the K in order to have a predictor. This particular function now becomes a predictor that will model, so to speak, this quantity for any given time t. So this is why it's so popular in science and all. Once you do your work and you decide that you have this model, instantaneous growth and decay, then you can do your experimenting and have a predictor. And so that can be very useful to your work. And as you communicate with your colleagues and all and clients, this can help you to support your case if they're actually paying you to do something. So we call this the predictor. Now, what I usually do with these kinds of problems is I actually solve for e to the k and change the base. But what we want to do first are just some simple examples where we don't have to work very hard just to get our feet wet. And we'll use our Google calculator to get nice approximations, but do everything exactly. So here's an example. Say, for instance, we're given that the K, and sometimes we call K by a special name. K is sometimes called the relative growth rate. Relative growth rate. So if you see this in a problem, that's what K is, relative growth rate. That's a phrase that's sometimes used to describe this proportionality constant K, as I've written right here. So in this case, we're given that K is 2%. And of course, we'll convert that to a fraction. So this will be 2 over 100, or just 1 over 50. So we're given K as a relative growth rate. And then we're given that in 2001, or excuse me, 2011, which will correspond to when we start recording time, t equals 0, we have y of 0, and this is actually a population, will be 120, and this is in millions. So basically, what we want to do, this is a population, that is, in this case, our y of t is measuring a population, and what we want to do is compute the population, assuming that we have the growth and decay law. Again, all the problems will tell you which law you're using. You don't have to come up with that. Compute the population in 2034. Now notice 2034 minus 2011. So that'll give us a 3 and a 2. This will correspond to the new value of t. So basically, we want to know this, y of 23 is what? And in this particular case, we assume, these are easy because they give you all of the stuff. We have to work harder with the other ones, but this is a good place to start. We assume the growth / decay law. These are great for populations, radioactive decay, things like that. This law is very useful. And it's proven to be very useful throughout history. That's why we continue to use it. So now we've got our solution curve, and we have our initial amount here. So we have y of t will be 120 e to the kt, and we have k is 1 over 50, so that'll give us t over 50. So the idea here is that when we do the k times the t, we're doing 1 over 50 times t, and that gives us t over 50. So this gives us a nice predictor model right here. So if you're given a problem where they actually give you k and the initial amount, you really don't have any work to do. That's the easiest problem. But this is a good place to start. So it's like it tells you in general, if you've got a problem to work on that uses the growth and decay law, you're always going to need to be able to figure out the k and the y sub 0, or e to the k if that's more convenient, that Professor Ron likes to do to change the base, so that we don't get a bunch of decimals and messy arithmetic and then mess up the problem with round off error. So this will imply that y of, in this case, 23, we just substitute 23 for t. So these are like some of the problems we did last week. Now, some of you were asking about this. This is the exact. And some of you were asking about this when you did your, what we call it, the continuous interest. So let me go over here and get the Google calculator. Google. Let me move this down here so the Zoom will see it. Okay, so we'll go back up here. So now we can use our 120, 120 times, and then we'll use our E, our natural base E, and then our power here, and then we substitute parentheses 23 divided by 50. And this will give us 190.08887. And in this particular problem, it says round to the nearest million. Let me just go back here and look at what this says, so we'll be sure to have this. Yes. So let me check this just to be sure, because I like to see what the WebAssign says. Let me go in and check. Let me move Professor Ron over. Okay, so let's see. Models. Okay. So in this case, let's see, that says round your answers to the nearest million. Okay, that's good. So I wanted to check that. So here, to the nearest million, this will be 190 million. So this will imply 190 million. So that's how you would type your answer. So again, the formatting is important. I'll write this in here, round to the nearest million. And since the output gives us millions, that's easy to do. We just get 190. Now, for the second part of the problem, it says, assume, for B, it says, suppose the relative growth rate is now 1%. And of course, this will just be 1 over 100. So now this will imply that our new predictor model will be 120, and now we'll have T over 100, E to the T over 100, whereas before we had 1 over 50, now we just have T over 100. And then in this particular case, if we wanted Y of 23, this would give us 120 E to the 23 over 100. So that would just be 0.23. And if you use your Google calculator, let's go and try that. So here we go. This up here. Oh, that computer's thinking a little bit. There we go. And let's see, where's my Google calculator? I'll have to find it in a second. Let me move this down here so it can see it. There it is. So clear this out, and this will give us 120, and then times, and then base E, and then your exponent, parentheses, 23 over 100, or you can type just 0.23. And this will give us 151.032. And of course, to the nearest million, that would be 151 million. Sometimes I get messages that you don't you're not getting, check marks and things, and it's formatting. So that's why I'm trying to be very careful about showing you about the formatting situations here. It's very important. It's not something that we just want to ignore. Now that was simple. Let's say that we've got something where we have a model, but we're given maybe less information. But we have to, we're actually given about the same information, but we have to answer different questions. So let's try this. Here's another example. And this is going to go back to some of the interest problems that we did. So in this particular case, we have a growth rate. I'll just write it out. Growth rate of K equal to 1.1%. And of course, this is just 1 1/10%, which is 11 over 10%, or just 11 over 1,000 if you multiply 10 by 100. And then we're going to have 2013 correspond to T equals 0. Another population problem, and Y of 0 is going to be 7.1, and this will be in billions. Now for this particular one, I'll go ahead and I wrote this down. We're going to round to 2 decimals when we do our Google calculator. Round to 2 decimals. For some reason, I had not written that down on the last problem, but I wanted to make sure what WebAssign said about the specific formatting, because that's something that's very important. Now, here's with that, this implies, again, that our solution curve will be the initial amount, 7.1 E, and now we have 11T over 1,000. 11T over 1,000. That's our solution curve right there. Now, here's the questions. We want to know the doubling time. Doubling time is what? For instance, if we're thinking about maybe population of the world, how long does it take the population to double? What's the doubling time? Just like we would say doubling time for an investment. So now this will just basically say, and if you want, we can just say this is Y sub 0. So we have 2 times Y sub 0. And you can write the number in, but this is more of a general rendering here. Doesn't really matter what Y sub 0 is because it's going to absorb. So twice the initial amount would be 2 times Y sub 0, and that equals this, which is Y sub 0, E to the 11T over 1,000. So we want to solve for T. Now what I'm finding, please do as I've taught you with all these problems. Don't truncate decimals, don't put in decimals, convert things where you keep your work exact. You're never going to have any success with these problems when you just, randomly truncate things and round to whatever. That is a catastrophe, okay? So if you learn by watching me during lecture or the SmartPen videos, you understand the technique, so please use them. It's frustrating when you don't, but I know you're not used to this, but I'm trying to help you get better. So now the Y sub 0 is absorbed. So we get, I'll just go ahead and write this exponential term on this side. E to the 11T over 1,000 equals 2. So you're thinking you could have just written this down because in general, the Y sub 0s or initial amounts we're going to absorb. So now we say, what's a logarithm? This is the power of the base. So So what we're seeing is that the power of E that equals 2 is 11t over 1,000. So 11t over 1,000 is a logarithm. So 11t over 1,000 is just the natural log of 2. And so now we can actually solve for t. Just multiply by 1,000 and divide by 11. So t equals 1,000 times ln of 2 divided by 11. Now, when you have this, if you work your problems out this way, then you've got an exact answer here. And you don't have to worry about your problem being riddled with errors. I mean, you could clearly just make a mistake here that is unwarranted, or that maybe it happens because we're human, but you certainly set yourself up for success if you do this correctly with an exact calculation. We do the same way in calculus and differential equations. There's no need to change. So now let's go here to our Google. The Google calculator is easy to use. It is a little bit, less refined, but it's got a great output. And you work this like you work your WebAssign. So now we have 1,000 times the natural log of 2, close, and then we just divide that result by 11. We don't need parentheses for this. So this will give us 63.01338. So that's approximate. And then, of course, we'll just round to 2 decimals. WebAssign requires, I'm going to say ask us, it requires that we round to 2 decimals. So this will give us 63.01 years. So again, here, T measured in years. So by this model, the doubling time for the population, if we're thinking of a world population, would be this many years. Now, again, if you wanted to do the tripling time, the equation would just change to a 3 over here. So let's just write that down and quickly write an answer. For the tripling time, this will just correspond to, if you look up here, we'll have 3 times y sub 0 equal to the y sub 0. So we get this equation with the 3. So this will give us e to the 11t over 1,000 equals 3. So now you're thinking you could just write a general formula here. You wouldn't have to, you could make a nice general formula for this. So this was just going to give us this. So now, if and only if, the power of E that equals 3 is 11t over 1,000. So 11t over 1,000 is a logarithm. So we're just basically changing out the log 2 to a log 3. But it's good to see this. So now we just get t, multiply the log 3 by 1,000 and divide by 11. And now again, when we do our computation here, we'll just switch out to a log. I could clear this and go back. There is a history, but that would take longer than just doing it again. So 1,000 times ln of 3, and then of course divide by 11. And so we see that we have a logarithmic scale. So this is approximately 99.8738, which will round to 99.87 years. So back to our document cam. So when we approximate, again, this is like doing financial calculations. You can set up formulas that would actually give you all of this without having to, you know, rework this. So as you work these problems, you're going to notice that you're basically generating formulas, and the financial calculations work this way. And some of you may do more with finances as your degree plans change and shift around. But I think it's kind of interesting that we see that we're doing the same techniques that we've been doing all along. Now, an interesting problem that basically says, okay, what about a situation where we just give you more information, but different kind of information? So I want to show you a way to compute with the growth and decay law in a way, again, that's exact, that does not introduce error. And this will be like a growth and decay with a radioactive element. So again, students say, well, how do I know which law to use? Well, if you're doing these problems, it will say obeys the growth and decay law or obeys the law of uninhibited growth. And if you, again, if it has to do with an initial amount and things like that, you can basically assume it's growth and decay law. That's the only law we have with these types of parameters. And then, of course, if it's about temperature, then that'll be the Newton law of cooling. So that there won't be any guesswork with that. You won't have to worry about that part of the problem. So now what we're given is 250 grams of a radioactive element, decays to 210 milligrams in 12 hours. And then what it says is compute this tells us a lot, but it's a lot less words. Compute the half-life. So the half-life is just the amount of time for half of the original sample to decay. So time for original sample to decay to 1/2 y sub 0. That is, you just basically get half. What's the time for half of the sample to decay? Basically, that's it. Half-life is a standard term in chemistry and physics and biology. And these are very useful things when it comes to dating objects. You know, archaeologists, biologists use these all the time. And this was really a big thing. And now with technology and laboratories that do everything for you, the instrumentation is so sophisticated. Now the math actually drives all of that technology to produce some really terrific results. I mean, you that are interested in the medical arts and all will have a very rewarding career. Again, many great things to do. So what we want to do here is first write down everything we know. We're going to use y again. So this implies that our initial amount is just 250. And so I guess, sorry about that. We don't want to just change from grams to milligrams. We'll start out with this. So milligrams to 210 milligrams. But don't worry about the units. But we don't magically just switch from one to the other. So forgive me for that. So y of 0, the original amount, will be 250. And that will be the mass of the sample. That is, the y of t is some quantity, and the original amount is 250. And then, of course, notice we're measuring t in hours. So after 12 hours, we have decayed to this amount. So y of 12 will now be 210 milligrams. So basically, we need t for 250 divided by 2 which is 125 milligrams. So it's going to be done the same way. We don't even have to use the numbers, just the y sub 0 equals the 1/2 y sub 0. The y sub 0s absorb and we're left with the 1/2. That's kind of like we did with the doubling and tripling time. So what I want to do is now we have y of t is equal to 250 e to the kt. And I want to show you a technique that is much easier than the way most of the textbooks teach it. And now, so we have our initial amount and we need to find a t, so we've got to find some way to replace the e to the k. So we can use this information here. 210 is equal to y of 12. So that'll just be 250 e to the k. Now we use our laws of exponents raised to the 12th power. So the key here is just simply saying, why bother to solve for k? If we need k, we can determine it. We know how to solve logarithmic equations, but we really just want to change the base to something easy to avoid having to go forward to go backwards. It's one of those things in math where you think, well, okay, why do I undo this just to put it back together? Sometimes we can't avoid that, but if we can, we choose the more efficient path. So now notice we have the 210 equal the 250 times the exponential raised to the 12th power. Now we want to solve, in this case, for e to the k. So now the zeros absorb, so we just get 21 divided by 25 equals e to the k raised to the 12th power. So now, of course, we can just take the 1/12th power of each side or take 12th roots. So e to the k is equal to 21 over 25 to the 1/12th power. So now this implies we can simply change the base here and then multiply the 1 over 12 by the t. So this says y of t equals 250 21 over 25, that's the e to the k, to the 1/12, and then we have t times 1/12, which is t over 12. So now we get a predictor model that has no decimals in it. And you don't solve for something just to go backwards. That never made any sense to me. And then, of course, when my students were doing the same thing you all are doing, truncating and rounding and getting ridiculous answers, I just decided, forget it. We're going to do it the Professor Ron way, and you're going to get the right answer every time. So now, notice here, if we needed to solve for k, we could just take natural logs of each side. But the problem's not asking for that, so we don't need to worry about it. So we're just going to change the base, and boom, there it is right there. Now we need, how long does it take for half of the sample to decay? So now we have half-life. This is kind of a nifty problem, and this is how most of the problems work. So now half-life will just be 1/2 y sub 0 equals, and now I'll just replace 250 with y sub 0. No need to just leave it in the abstract. So now the y sub 0 is absorbed. So this is really where you could just say, I'll just set the power equal to 2 to the 1/2. So 1/2 is left over, and that's just 2 to the minus 1 equals 21 over 25 t over 12. Now, what's interesting about this, and what is a good way to look at this point, is like, okay, I've talked to some of you about this during my conference hours. We don't want to use base 21 over 25. That's kind of ridiculous. So we can just take natural logs of each side to bring the power down, and like we did with our interest problems, just to keep our sanity. So now take natural logs. So the natural log of 2 to the minus 1 Of course, the minus 1 is going to come down by the power rule, equals t over 12, again, power rule. I could have brought that down. This is easy to see. Bring this down. So we have natural log of 21 over 25. Now, of course, the power rule here, this is just negative log 2 by the power rule. So now we solve for t. In this case, we multiply by 12 and divide by the natural log term. So now we have t equals negative 12 times ln of 2 divided by the natural log of 21 over 25. So again, when you look at this is just, and look at it as t, and then you got the ln of 21 over 25 divided by 12. So you flip it to multiply the negative log 2 by 12 over the log term. And that's the actual time, that's the half-life right there. This is exact half-life. So when you get to calculus and differential equations, this won't change. You'll be doing the same calculations we're doing here. And trust me, when I teach differential equations, I remind them of this technique. And they're like, oh, we didn't do it that way. I said, well, if you didn't take me for pre-cal, then now you learn it. But of course, the ones that had had me for pre-cal and all the calculus were teaching all the other kids how to do it correctly. So now you look at this and say, we can go to the Google calculator. And in this case, WebAssign directs to round to the nearest whole number. Whole number. So again, this will be in years. So let's go to our Google. So again, and this is, don't be surprised if you see a WebAssign problem that says, give the exact answer. So that's what you have to type. I'm giving you a break right now that you can use, but I mean, that would be a better answer right there. That would tell me that you knew what you were doing. And so now we have what, negative 12. So let me get my, oh, there we go. Negative 12 times ln of 2. So we have ln 2 close divided by ln, use your parentheses. Well, I don't need extra, sorry, clear that out. 21, because it's built in, 21 divided by 25. And this gives us 47.7063. And of course, to the nearest integer, that will be 48, in this case, hours. Now, of course, this wouldn't be a good element for dating artifacts because the half-life is too short. We have to do half-lives that have, you know, years, you know, really large numbers of years. So that's why other radioactive compounds are used to measure that. It's amazing. It's amazing the chemistry and the biology and the mathematics all come together to produce wonderful, wonderful technology that again transforms our lives. So this problem is more or less showcasing the power of the growth and decay model. That is, in most examples, you would be given an original or initial amount, and then some information about decay. That is, after 12 hours, you have this much sample. And then, of course, that would be enough information to compute the half-life. Again, we need the original amount, or at least something that will allow us to work with this. You're thinking here, we didn't really need it. I mean, because there's nowhere in the calculation except here. For instance, when we solve for e to the k, that was useful to have it there. But once we have e to the k, we don't really care about the original amount. So sometimes we can avoid the use of it depending on what's given to us. Notice here, again, this is an important technique. If you want to get a nice predictor model, instead of solving for k, solve for e to the k, and then just replace e to the k with this number and multiply the power by t. So you get a nice simple formula, no rounding, no decimals. Now, if you're given a k and all that, and WebAssign says just type it in, fine, that's different. They give you the k, and the decimals that they give you are exact. So because they're given in the problem. So if you have to do that, fine. That's not what I'm saying. If you're given a problem like this and you need to write down an actual predictor model so you can actually find the half-life, this is a better way to do it. That way you avoid all the unnecessary rounding. You have an exact answer here, which will then give you the best approximation possible. So this is the way to do it. This is the clean way to do it. This is the correct way to do it. If you have learned another way, then unlearn it and do it this way and do it correctly. Again, the precision that we have in math must be supported by good methods. Just roundabout punching on a calculator whenever is not going to cut it anymore. And I know that many of you were raised with a calculator, and that's unfortunate. We use a calculator as a tool. We don't use it as a crutch. We use it to push our knowledge forward, not to be a substitute for our brain. Now, let's look at an example. This actually was an interesting problem. Again, you can do all kinds of examples, but this one is what I was talking about. Say we were using a radioactive compound that had a much longer half-life. Say we're archaeologists, and in this problem we found a wooden artifact. So this will be some of you biologists and science majors will identify with this. The thing is, when you see these in biology class, especially, I had a professor one time when he taught genetics, he said, go see Professor Ron because I can't solve quadratic equations very well. So they all came to the office to learn about the binomial distribution. And I said, okay, kids, this is college algebra. They said, well, tell us what to do. And I said, your professor really knows how to do this. I think he just wants you to maybe see a math professor do it. But again, you see all of these problems in science. So now you know how to solve them in a more elegant and precise way. So here, again, we have the growth decay model. So write that down, growth decay model. And we've located a wooden artifact. A wooden artifact. And this wooden artifact has 70% of the carbon-14 present in living trees. So basically, the carbon-14 is decayed to 70% of its original value in the living tree. Okay, so that's really useful right there. That's good information. And then it says, you're thinking, okay, so we need a half-life, right? And then you're going to say, how old is the tree? So basically, we'll say, when was the artifact made? So we're going to figure out how old this thing is. When was the artifact made? How old is it? And then, of course, a little piece of information, which would be very useful, is the half-life of C14 is, and this is more in line with what you would want, 5,730 years. So, and WebAssign, of course, says round to the nearest whole number. So let's go ahead and write that down. Round to the nearest whole number. You need to make sure that you pay attention to all of the formatting, because you do all of this work and then you get frustrated and you send me a message saying, I don't know what's wrong with WebAssign. And all I can do is look at the answer and say, well, they told you to round to the nearest whole number and you typed in 2 decimals after the ones digit. So they're easy to spot, and it's easy to ignore this because you're focused on other things. But maybe just write that down at the beginning so you won't forget it. So now we think of this like, okay, so we have 70% of the original amount. So basically, let's write down the actual equation. So we have y of t equals, in this particular case, the original amount, e to the kt. And notice we've got 70%, which is 70 over 100, or 7/10. So that's the percentage of C14 that's left. And 1/2 of the original amount will be present after 5,730 years. So we have 1/2, so we go over here, 1/2 y sub 0 equals y naught e, want to solve for e to the k, e to the k, 5,730 years. So in 5,730 years, half of the C14 will have decayed. So you're thinking, just forget the y sub zeros. So if and only if 2 to the negative 1 equals, in this case, e to the k raised to the 5,730. Now, this is interesting. You're gonna take the 1 over 5,730 power of each side. kind of interesting the way the numbers work. So now, if and only if e to the k will just be 2 to the negative 1 over 5,730. So the idea, ladies and gentlemen, is that when we take the 1 over 1 over the 5,730 power of each side, we multiply here with the exponents and get the negative of that. So we use the laws of exponents over and over. So now this implies that we have a predictor model. So now y of t equals y sub 0, and then we have 2 to the negative t, multiply the t by the power, 5,730. So there's our predictor. So now, how old is it? Well, now we know that 70% of this exists now, presently. So now, 7/10 of the original amount now exists. Again, I won't just put 7/10. I'll just go ahead and let the y sub zeros absorb. So now we have 70% of the original C14 is present. So we want to see what time that corresponds to. So we have 7/10 of y sub 0 equals our predictor. That is y sub 0, 2 to the negative t over 5,730. So now the y sub 0 is absorbed, and we just get 7/10 equals 2 to the negative t over 5,730. Now, just like before, you could take a base 2 logarithm here, but since we're going to have to approximate, go ahead and just take natural logarithms, just like we've done before, to just make it a little bit easier. Take natural logs. Again, base 2 is fine, but the Google calculator doesn't do base 2, so we'll just go ahead and do base E for ease. So we have ln of 7 over 10, and now take the logarithm and the power rule, so that gives us negative t over 5,730 times log 2. So again, the natural log just makes our computation a little bit easier. And so now we can solve. Multiply by 5,730 and divide by log 2, and with the negative sign, of course. So t is equal to negative 5,730 times natural log of 7/10 divided by natural log of 2. So again, just like before, we have a situation where we have an exact time, which gives us the age of the artifact. That is, when was it made? How many years ago? And so this is like a birthday, so to speak. And so again, these are the more standard problems because again, they just require that you know the model, the solution curve. You write down what's given, and then this is where the half-life is extremely important. That is, this will allow you to find e to the k so you can write a predictor model with a changed base with no rounding whatsoever. And now we use the given information here, which tells us that 70% or 7/10 of the original amount of carbon-14 is now present. So how does that impact everything? Well, now that allows us to solve for t because the y sub 0 is absorbed. And then what we're seeing is that we don't even need to know y sub 0 in this case. It wasn't even important. This is where we actually could work the problem without it. And so now, as we move forward, taking natural logs, we have the exact age of artifact. And this way you have a nice clean formulation. So now we can go to our Google calculator and then of course round to the nearest whole number. These are fun when you think about it. This should bring out the science in you. So now we have negative 5,730 times natural log, and we'll do 7 or 7/10, 7 divided by 10. You can do 0.7 if you like, divided by natural log of 2. And this will give us 2,948, approximately 2,948.50. So to the nearest whole number, that will be 2,949 years. So again, when it comes to doing the carbon, you hear this in the terminology and the speakeasy of scientists. They say carbon dating showed. Okay, now of course this is not like precise down to the millisecond. It's not like a computer time. But what we see is that we get a really, really good ballpark figure of the age of something. You think about the archaeologists when they use the carbon dating with the tombs of the pharaohs and in Egypt and things of that nature. So the science and the math mix together to provide information that is very, very useful. And I guess it just makes us all scientists at heart, but we all have things we like to do. Some of you like to do the lab work. Some of you like to do the site work. You go out to the site and you collect the information. You like to be the mad scientist. Some of us like to take the information and work with it. Others of us like to fashion and create the mathematics so you can work with your data. It takes all kinds of team members with different interests to get a product that is useful for your clients. So again, all of you, you don't have to have the same interest. We don't want you to have the same interest. We want you to have varied interests so that all aspects of our society will continue to function. If we all wanted to do the same thing, we really would be in trouble. So some of you want to be medical doctors, some of you want to be computer scientists, some of you want to be engineers, some of you want to be dentists. I mean, it could be any number of things. Now, and one thing is not any more important than the other. The main thing with the STEM education is that you find something that you actually enjoy doing, and you know that's difficult. You may like something, but you don't think, well, I don't want to do this every day. So that's a really tough decision. So don't worry that you're still in the mode of processing everything. That is natural, and you should be thinking that way. Now, the other model is called the Newton law, and it's called the cooling law, but it really doesn't really mean cooling. It could be heating law or cooling law. The sign of the growth rate type thing, the K that we talked about in the growth and decay law, will actually determine what happens in this particular model. So don't feel like you know, just remember that whatever model you're working with, if WebAssign asks you to respond to something, make sure you also use some common sense. So this is called the Newton law of cooling. So you could think of an object as being heated and then cooling. Okay, that's probably what we end up doing the most. And so that's probably, as Newton, you know, devised this law, but it could go in the other direction. The object could actually be heating, and it'd be the same process. So I don't want to discriminate against other processes by saying, oh, the power must be this. That would be a very weak law that's not very flexible. So here's what we're going to say. We're going to say this is a notation Professor Ron will use, but always use the notation of the problem. We're going to say U of t corresponds to the time-dependent temperature of an object. Time-dependent temperature of an object. So, you know, whatever the object is, maybe it's something you cooked in the oven. Maybe you work for the crime unit, you know, and you're trying to figure out the approximate time of death. I mean, the Newton law of cooling is very useful, and maybe not always in the most auspicious circumstances. I mean, there are times when it's used and it's not a very pleasant situation. So for instance, we have time-dependent temperature of an object, and what we're going to do is we're going to let uppercase T be the temperature of the surroundings. Temperature of the surroundings. And then let's see what else. We're going to have U sub 0 will be the initial temperature, just like we have Y sub 0. Initial temperature of object. And then, of course, we're going to have the K, which will be the proportionality constant. Before we called that the relative growth rate. So K will be proportionality constant. So the Newton law of cooling, really the solution curve looks a lot like the solution curve for growth and decay. Not a big difference. Law looks like this. So this, again, this is a differential equation. So we could say the instantaneous law of cooling, really, because it's based on a derivative. So we're saying the instantaneous rate of change of the object temperature, which is du dt, is actually proportional to the difference in the object temperature and that of the surroundings. Sometimes they use S for surrounding temperature. Sometimes instead of U, they use a T. I like to use the U since the little t is for the time, and then the big T is for the temperature of the surroundings. But I mean, you can use any letters you like. It just really depends on how you feel that particular day when you write a problem. And then of course, the solution curve. And of course, we'll have an initial temperature of the object right here. So like before, we had y sub 0 equals y of 0, which was the initial quantity. This will be the initial temperature. And so we see that Newton devised this law, that as an object cools or heats, that the cooling rate is actually proportional to the difference between the temperature of the object and that of the surroundings, which really kind of makes a lot of sense. If you think about it, we observe this every day in our lives. Now, what does the solution curve look like? Well, it looks like this, and this is not a surprise. This will be the temperature of the surroundings plus this exponential term, u sub 0 minus t e to the kt. So you're thinking in some of these problems, instead of finding k, we'll just replace e to the k and change the base. So now what you're seeing here is that this term will actually decay of necessity. The thing is, and so, you know, the value of k will be dependent upon the problem. But if you place an object, heated or cooled, into a room of temperature T, after a certain amount of time, the object temperature and that of the surroundings will equilibrate. That is, this term will decay. And that's what we know. I mean, you know, you think about you drive up to San Jac when we could, and you know it's 100 degrees outside, and your car bakes in the sun, and then you come back to your car after class and you burn your hand when you try to open the car door, or you sit down on leather seats and you're like, that was a mistake. Maybe you get home at night and you throw a pizza in the oven, and you take it out of the oven. You don't eat it right away because you want it to cool, so you leave it on top of the stove for 10 or 15 minutes to cool, and then you eat it. So we really do depend on this law. I mean, we observe it every day. This term has to decay. So the Newton law of cooling is probably much more intuitive to us than the growth and decay law. So I think when Newton devised this, he probably thought, well, I'm glad I have some mathematics to support what we experience every day. So now let's look at some examples. Now, when it comes to the cooling law, one of the nice examples, and I like what WebAssign does here. It actually gives you a value of K that we can use in our formulation. So it's not as difficult as the last problem we did, but it's a very useful problem. Say you work for the FBI, or you work for the crime unit, and you've got to do some rather gruesome science to figure out the time of death. So for instance, here we have, like, we call this a homicide investigation. So what we have here, let's just write down some things we know. The standard body temperature, we all know that. The standard body temperature is 98.6 degrees. So we'll just say 98.6. We won't worry about, this is Fahrenheit, but we'll just leave the numbers as they are. And then we'll say upon death, the body begins to cool. And it actually, the cooling of the body obeys the cooling law by Newton. The body begins to cool. Now, the thing is that this requires some experimentation. That is, you have to do some research to figure out the relative growth rate. And so we'll just say experiments show in this particular case, so this way we won't have to change the base this time. Experiments show K is 1,947 divided by 10,000. That is, it's 0.1947. So experiments show this for body cooling. And then T is measured in hours. Now, what we want to do is the following. For instance, we find the body. The body is located. The body is located, and T equals 65 degrees. And then what we want to do is we want to consider the time that the body has actually been in that deceased state. That is, compute T for the deceased state. So now what we have in this particular case, and we want to just go ahead and write down a law. So let's do the law first. That'll be the first part. So we have U of T will be the surrounding temperature, which is 65. We just follow our law, 65. So you need to put these on a note card or commit them to memory, plus 98.6 minus 65, and then we have E to the 1,947 T over 10,000. So that's our curve. And now this is where we have to look at this and make one estimation here. The actual K here, and the way it should be given in the problem, is that this should be a negative, because this is going to have to decay. So that's a negative. So here I'm going to, and WebAssign may not give you this, but it's actually, our K is actually negative because we need decay. So what we could see here is that over time, this term will converge to 0, and the body temperature will be that of the surrounding temperature. So now let's go ahead and reduce this. So we get 65. And then of course here we get a 0.6. And then we have a 3. And then we have a 3. So we have a 33.6 E to the negative 1947 T over 10,000. So the key here is if a K or a value of K is given, and you know that the body is actually cooling, so to speak, this term must decay. So somewhere you have to make the leap. If WebAssign doesn't give you the actual sign, that's just the way the problem is set up. And I think maybe they're trying to trick you. But you can follow what Professor Ron has done and have the right sign here. So now you can look at this and say that as time goes on, time progresses, becomes large, this term, as we've seen before, this is a nice decreasing function. This will converge to 0, and eventually the body will be 65 degrees or approximately 65 degrees. So here's our law of cooling. And again, with the homicide investigation, you must be given a value of K that's experimentally determined. That will be something you have to have. And now B, like I've said here, compute time of death, or the time for the deceased state. So now what we want to do is, in this particular case, we're thinking, all right, well, here's, we find the body, we find the body, and observe U of t equals, this is what Webber-Stein gives us, is 76 degrees. Okay, so obviously it has cooled from 98.6 to 76. How long did that take? So this is where we use the law. So now we use this and solve for t. So solve for t. This is a much easier problem, but there's just a little bit more given stuff. And so we're more dependent on the actual hypotheses in the problem. So now we have 76 equals, move the paper up a little bit, equals 65 plus 33.6 e to the negative 1947t over 10,000. And so now we want to solve for t, so let's go ahead and subtract. That'll just be a 1 and a 1, so we get an 11 here. And then we can go ahead and divide by 33.6. So subtract and divide. And that gives us e to the negative 1947t over 10,000. Now at this point, we're good to go. We didn't change the base, so we'll just do natural logs. If and only if natural log of 11 divided by 33.6 equals negative 1947t over 10,000. So now, like we did before, we multiply by 10,000 or negative 10,000 and divide by 1,947, the log term. So if and only if t equals, you can just move the negative downstairs with the 10,000, it doesn't matter, negative 10,000 natural log of 11 over 33.6 divided by 1,947. So now this is the exact time. Basically, when an officer is, when they say compute the time of death, they're basically saying how long has the body been in that state, the death state, the deceased state. Not basically like, oh, it was at this time. And then you can extrapolate the time from that. But they're basically saying, how long has the body been deceased? And that's what they're referring to. So that's what I mean by the T for deceased state. So now we can go over here to our Google calculator. And we have negative 10,000. These are fun. I mean, you have to admit, these are kind of fun problems. It's like we're having fun time today working with the science problems. 11 divided by 33.6. They're easier than doing complicated algebra, so it gives us a break. And then we divide by 1,947. And this gives us 5.735. And in this case, we want to round to, let me write this down, round to the nearest whole number. I didn't write that down originally. So WebAssign declares round to nearest whole number. So this will give us 6 hours. So we find the body and we observe through our calculations that the moment of decease state occurred approximately 6 hours ago. So we're thinking, okay, the foul play occurred then. Now we need to check all the other evidence and see what the crime scene tells us. So basically, you know, if you do have friends that are in the science of criminology and all, we have a degree like that at San Jac. And then, of course, a lot of these individuals go on to become police detectives, work in investigations, a very, very fascinating career. I would think working for the FBI, no day is a dull day. I mean, if that's something that you really like, it can be a fascinating career, but very high paced. So again, we can use the Newton law of cooling to actually determine the time for the deceased state. And this actually is very useful. But again, remember, when you're doing this kind of problem, you need the value of K that has been experimentally determined. So that is one kink in the process that you need, kind of like when we did the radioactive decay. We need the experimentation that says, what is the half-life of carbon-14? If we don't have that, if we don't have the biologist doing the experimentation, the mathematics is not going to provide us good results. So everybody depends on everybody else. We depend on Professor Ron to compute things correctly, but Professor Ron has to have good input. So I have to depend on my colleagues. You know, you depend on your colleagues to give you good data. So what you produce is actually good. So now, let's do another example, since we always eventually end up talking about food as we get into the season. You know, we do the Halloween, which whatever, and then of course Thanksgiving and things like that. So there's always good time to talk about, you know, cooking things and knowing about the cooling law. So here's an example that doesn't have to deal with homicide. Maybe it's a little bit more pleasant. So we'll say a turkey is removed. Turkey removed from oven an oven at 185 degrees. The kitchen temperature is 71 degrees. Okay, and then it says, so, and what we're going to do is T measured in hours. So we'll agree that measured in hours. So we have a consistent time dimension. So for A, we're given that after 1/2 hour, and let me use the notation that I gave you. After 1/2 hour, U, and so we'll just say U of T is the temperature of the turkey. So after 1/2 hour, the turkey temperature is 150 degrees. And we're asked to compute the turkey temperature after 45 minutes or 3/4 hour. So we'll say U of T corresponds to turkey temperature. So now we just have to fill everything in. So our curve, the law, will actually, the law states through the curve, that is, let me just say here, let me write it like this. From theory, that'll be an easier way to say it. From theory, we have a solution curve that is U of T will now be the surrounding temperature, 71, plus, again, the initial temperature. When you take the turkey out of the oven, we have the 185, which is the initial. So I can write here initial temperature is 185. So we have initial 185 minus that of the surroundings, which is 71, e to the kt. So equivalently, u of t equals 71. And so now we've got a 4 here, and then we've got a 7. So that's 114 e to the kt. So here's our predictor, at least as it is right now, but that's not very good. We need the e to the k. So now we want to solve for e to the k. So we can rewrite this. So we have u of 1/2 equals 150. So 150 equals u of 1/2. So we have 71 plus 114 e to the k raised to the 1/2 power. So when you think about these problems, you're just using the laws of exponents and getting the part of the equation that's going to move it forward. So now we can say, okay, well, we can just subtract. So we have one, well, if we had 70, that would be what, 80. So 1, that gives us what, 79. So 79 equals 114 e to the k to the 1/2. I'll do a couple more steps here. I kind of did the last one a little bit fast, but I'm just thinking about time. So now we've got 79 divided by 114 equals e to the k raised to the 1/2 power. So now we can just square both sides. So we have e to the k equals 79 over 114 quantity squared. And we won't do anything to that, just leave it alone so we can keep the powers nice and clean. So now this implies that u of t will be 71 plus 114, 79 over 114, 2t. So don't try to absorb anything, because this is the law and it preserves the 2t. And so don't get, don't do something that's just going to rip this apart. So leave everything alone. So now u of 3/4 will just be 71 plus 114, 79 over 114, and 2 times 3/4, 2 times 3/4. So the 2's will absorb into the 4 to give us a 2, so that'll give us a 3/2. So this gives us 71, oh, sorry, I don't need the plus too soon. 71 plus 114, 79 over 114 to the 3/2. And that's the exact temperature after 45 minutes or 3/4 hours. This is exact. Now, I will say this, with the growth and decay, you don't have as much arithmetic, but the arithmetic is pretty simple. Just again, keep everything exact, don't do any approximating. And so now we can go to our Google calculator. And in this case, let me see here, round, let me go ahead and write this down, round to nearest whole number. Okay, so let's go to Google. To our Google calculator. And so we have 71 plus, and now we have 114, 114. This is so nice and easy to use, and 3 times, now parentheses. So we'll do 79 divided by 114, close, and then now we want to use our power key, and then parentheses, 3 divided by 2. So the calculus, the infinite series give us these beautiful, beautiful approximations. The calculus and the infinite series is what makes these calculators work. And you're going to learn about that in calculus too. So there comes a time. So this will be approximately 136.76, which will give us to the nearest whole number, 137 in this case. So let's see, degrees. So of course you expect it to be cooler, right? Because again, more time has elapsed. After a half an hour, well, let me go back to the document cam. After a half an hour, we have 150, and then we use, we use that to actually, once we have this, for instance, we've got the original temperature, 185, of the turkey, the surroundings to get this. Then to get the e to the k, we use the given information here. We solve for e to the k, we just get 79 over 114 quantity squared. That's easy. I mean, these numbers are easier than the last one with the 5,730, whatever. And so now when we substitute, we have an exact equation for which we can substitute 3/4. So now it makes perfect sense. I mean, this is a way we can check to make sure that our approximation is at least consistent, and it continues to drop. So after an additional 15 minutes, the turkey is cooler. So again, this is just what you do. You take something out of the oven, you don't eat it right away, you let it cool, or you burn your tongue. I mean, you know, everybody has different, you know, levels of what they can stand with heat and all of this, spicy heat or you know, temperature heat. So again, this is something we experience every day. This is now just the mathematics behind it. So you can always strike up a good conversation at, I don't know, at a reunion. Maybe you just end up clearing the room if you start talking about math. Okay, well, but you know, it's all good. So B, it says, let's see, what do we have here? Okay, so now here's what WebAssign gives us. It says that the temperature of the turkey is 100 degrees. So you're thinking, okay, it's even cooler than it is here. And then they say, what's the time that has elapsed? How much time will have elapsed if the temperature is now 100? Okay, so this is exactly what we've done before. This is like finding half-life or tripling time. So this is a simple problem. So now we say, okay, we have our predictor right here. So we just set the predictor equal to 100 and solve for t. So this implies, or equivalently, 100 equals 71. When you got this nice predictor model, ladies and gentlemen, you have clean calculations. Anything but this won't work and will be full of errors. So I'm saying if you adopt this procedure, you can teach this to your friends and they'll be in the know too. So 71 plus 114, 79 over 114, 2t. Solve for t. So again, we'll use natural logs because again, the base 79 over 114 is a legitimate base, but we won't worry about that. We'll keep it simple for our Google calculator. So now when we subtract, if you see here, we've got 30 minus 1, which is 29. Now notice if we subtract the 71 from the 100 and then we can divide by 114, I'll break this up into two steps. I know I did it on that last problem, so I'll just break it up into two steps. So now divide by 114. Keep everything exact. I know, like I say, this is new for a lot of you, maybe for all of you. So now, again, just like we were doing the half-life problem, we can take natural logs here. So we have equivalently natural log of 29 over 114. Again, use the power rule. That'll be 2t natural log of 79 over 114. And so now here, if we look at this, we can divide by 2 times the natural log of 79 divided by 114. So the thing is here is that we don't have fractions like we had before. So now t equals the natural log of 29 over 114. And then, of course, you could devise formulas for this, make up your own formulas. And then 2 natural log 79 over 114. So the key here is, again, exact calculation. And then with the, let me do the focus, get that cleaned up a little bit. Now with this, again, we can easily approximate, no worry about round off error. But I will say with these problems, these are kind of like doing calculus 1 and calculus 2 problems. There are lots of steps. There are lots of places to make mistakes. So you have to be careful. And if you don't get a check mark, then don't just assume you did it wrong. Check for some of the obvious things. Check for the rounding, the formatting. Check for typos. I mean, there are many things that, like I say, the WebAssign will train you, but it will be a taskmaster at many times. So now let's go to the Google calculator, our friend, our free scientific calculator. So we have natural log of 29 divided by 114. So the only time we pick up the calculator is at the very end. Now we need parentheses because we're going to say, excuse me, clear that out, divide by parenthesis 2 times natural log 79 divided by 114, close. And this will give us 1.86625, approximately 1.8. The calculus that makes our calculators work is amazing. Again, calculators are coded so that they utilize infinite series. Again, a major breakthrough that we developed the technology to use the calculus. So if we round to the nearest, in this particular case, they changed the formatting here. They say round, for this part B, they say round to 1 decimal. And so this will give us 1.9 hours. So again, this is where you can look at your work and compare it to what you've done. That is, does this make sense? Okay, yes, it does make sense, because after 3/4 of an hour, we find the temperature is 137. So to get to 100 degrees, another 1.9, well, basically, if you do 0.75, that's like another hour, 1.2 hours to get to this temperature of 100 degrees. So again, everything is consistent. If you do your calculation, and you get a strange looking number, maybe there's a typo. Maybe when you did your approximation, there's a careless error. Lots of times we forget parentheses. So So like when I do this, I really have to think, okay, I'm dividing this number by this product. So when I entered this, I had to use parentheses here. Again, the problems, especially with these, are preparing you for the calculus when you have multi-level, multifaceted problems. And we're going to find that to be the case in some of the trig problems that we do. Lots of steps. And the steps are what prepare you for the long differentiation problems, limit problems, optimization, Riemann sums, and then especially in calculus 2, where you do applications of the definite integral, you do techniques of integration, infinite series, all kinds of interesting problems, polar integrals and things where you have step upon step upon step. And so this is going to be good preparation for that. I will tell you that you will add some calculus to this, but these calculations here, you will continue to do, and this gives you a nice blueprint to do your calculations as you get into your more advanced calculus courses where you have nice clean computations. The key, ladies and gentlemen, is clean work, is work that is devoid of excessive approximation. That is the issue here. We want to be able to do exact work and keep our computations clean as much as we can. There's some cases where I think we've decided that since we have technology, we don't have to worry about that anymore, but that's not the case. That has actually put some students back into a corner where they don't have the proper skill set. They got the intelligence, but they need the proper training to use that intelligence to do some really good work. And that's what I'm trying to help you all do, because you all are very bright, and I want you to have good techniques so that you can share your techniques with your friends and teach other people to avoid excessive round off. Now, we're done. Say goodbye to the exponentials and all that. So the next thing we're going to do will be trigonometry. And then if you go to your Blackboard site, you have the Professor Ron unit circle, and I coded this in LaTeX, and I decided with this, I did this many years ago when I started at San Jac, and I added the degree measure, and of course I wrote the 1 over root 2 as rationalized form, but I'll never use it that way. I'll just do 1 over root 2. But I went ahead and put some colors in it. So I guess as we get to the holiday season, this might make more sense. But I used polar coordinates to actually code this, and then I thought I'd just go ahead and fill in with some colors here. So if you don't like the colors, you could print this out in black and white or just bring it up on your screen. But again, this will be something you can use as you work your test. You may have your own unit circle, but this is something where we're headed. We're going to start with the unit circle and form our trigonometry based on this. And then after we get that, we're going to look at right triangles, which can be imposed on the unit circle. Okay, well, thanks for your attendance today. And like I say, on Thursday, we'll start trig. So get busy finishing up your exponents and logs. And then of course, next week we'll have our first test or our second test. And so I will be posting some information about that, the same format, and I'll give you a similar window of time so you have plenty of time to take your test as we did for the first. So you all have a great day, and I'll see you. Sorry for going over. I'll see you on Thursday, or if not earlier, at my office hours. Bye.
Thank you.
Thank
Good
you.
day, sir.
You too.
Thank you.
Thanks, everyone.